We talked about electron configurations. There's some weird ones. We've been talking about electrons and valence electrons because they're the most important. Whenever two atoms bump up against each other, those are the things that interact. And how those electrons swap, change places, form bonds, those are the properties of that element. So these valence electrons are the reason that the periodic table is set up the way it is. And so we have families of elements represented by columns on the periodic table. And all of the elements in 8A, they're the noble gases because they don't react with anything. And the reason that they don't react with anything is because they have 8 valence electrons, except for helium, which is 2, because it's small and it only needs 2. The rest of them, though, have 8. And because they've got these 8 valence electrons, they've got completed orbitals, completely filled orbitals, which is especially stable because of quantum mechanics. So take quantum mechanics if you really want to know the why. And this also gives us what every element, if we can think of elements as having desires, all of the elements want to be like the noble gases. So they want to gain electrons or lose electrons to be like a noble gas. So if we move in any direction away from the noble gases to the alkali metals, for example, which, looking at the periodic table, might not feel like they're next to the noble gases because they're on the opposite side. But remember, the only difference between sodium and neon is 1 proton and 1 electron. So really, it's taking one step to go to the other side. There actually, I've seen some periodic tables where it's, instead of being flat, it's like a cylinder. And it continues in this spiral that goes down. And every 8 elements or every so many elements, it like comes back to the noble gases. So you still get these columns, but you can see better that noble gases are really close to alkali metals. Although even in properties, they're very different. All right, so alkali metals, they want to lose 1 electron. Because if they lose an electron, then they'll have the same electron configuration as a noble gas. So if I did like sodium's electron configuration, 1s2, 2s2, 2p6, 3s1. And if I write that with neon, make sure I'm doing the right one. This is 1s2, 2s2, 2p6. So neon or sodium has 1 more electron than neon. And potassium would have 1 more electron than argon. And you can keep going all the way down. So what happens is when you lose 1 electron, you get a 1 plus charge because now you have 1 more proton and you have electrons. So the reason that the alkali metals all form 1 plus charges is because they're only losing 1 electron to get to a noble gas electron configuration. All right, so if we move over 1 more column, oh, sorry, got this in the other order. Going back over to the noble gases, if instead of going to the right and adding 1 proton, we remove 1 proton, then we get the halogens. So the halogens have 1 fewer electron than the next noble gas. So comparing any of these, so if we compare fluorine, which is going to be 1s2, 2s2, 2p5, and I compare that to the nearest noble gas, which is neon, 2p6. Fluorine only needs 1 more electron to have the same electron configuration as neon. But then that means that there's 1 more electron than there are protons. All of the halogens, similarly, just need 1 more electron. And so they'll form a 1 minus charge. Should be reviewed so far. I think we're going to talk about the other. Oh no, actually, we're not going to talk about them. There's other groups. So like group 2A are the alkali earth metals. They lose 2 electrons to get a noble gas configuration. Group 6A needs to gain 2. So that's oxygen, also called the chalcogens. So again, they're all forming these ions because they want a certain number of electrons so that they match the noble gas electron configuration. So those are all a lot of the predictable charges. There's some other ones on here. So nitrogen almost always forms a 3 minus because if it's here, it needs 1, 2, 3 more electrons to to have a noble gas configuration, which means it's got 3 more electrons than protons. Yeah. And aluminum will predictably lose 3 electrons to have the same electron configuration as neon. So those are why those are useful ones to memorize. Oh, and this is, I already talked about this, but anions are formed when nonmetal atoms gain enough electrons to have 8 valence electrons. So I showed you with fluorine how it gains 1 electron to have the same configuration as neon. Sulfur wants to have the same configuration as argon because that's the closest noble gas. So it gains 2 more electrons, and that's why it forms a 2- ion. So they're just gaining or losing electrons so that their highest energy electrons are in a complete orbital or complete shell. And then for the cations again, they're losing electrons. This will come up later when we talk about electron affinity, but the process is endothermic. And so we have to lose an electron. That means we're taking an electron from a lower energy state and moving it away from the nucleus, which puts it into a higher energy state. So it takes energy to remove the electrons. So like magnesium has only 2 valence electrons, but it can lose those, give them up to some other, probably non-metal that wants them, and then it'll have the same configuration as neon. Okay, so how does all of this relate to atomic size? This is the first trend that we're going to talk about, and we'll talk about atoms first, and then we'll talk about cations, and then, or I think anions and then cations. When we're talking about atomic size, it's the non-bonding atomic radius, or van der Waals radius, which is just half the distance between adjacent nuclei in the atomic solid. So if you made a solid material out of any element, we're just measuring the distance between adjacent nuclei. There's some overlap like this picture shows, but it's a convenient way to measure. Or we could use the bonding atomic radius or covalent radius, which essentially ends up being the same thing. Sorry, in the covalent radius, we lose a little bit because of the overlap. So half the distance between the 2 atoms bonded together, essentially saying if this is 228, if I cut that in half, then each atom is reaching out from its nucleus half of that. You don't have to calculate this, it's just so you know it. So again, we can measure these for different types of elements, but in general, we're talking about the distance or the size of the atom's radius. So from the nucleus to the outside of its highest energy electrons. Yeah, it's really all it is. How big of a sphere does this, how big of a sphere is the atom? And since we're measuring here really the distance from the nucleus to the electrons, any changes to the electrons is going to change that distance. Or actually, in some cases, changes to the core number of protons. This chart's a little bit hard to read, so atomic radius increases down a group. You might be thinking, it looks really weird. So the way that this is set up is that these are just ordered by atomic number. So this would be hydrogen, helium, and then we go to lithium, and you see there's a huge increase in size because we add a higher energy shelf of electrons. And then the size decreases as we go across the periodic table, and then it jumps up again, and then it decreases, and then it jumps up again, and then decreases. So if we want to compare a family or a column of elements, like helium, neon, argon, krypton, and xenon, those are all the noble gases. And so we say, looking at helium, neon, argon, krypton, and xenon, the size down that group increases. Or if we looked at the alkali metals, which are much larger, sodium is larger than lithium. Potassium is larger than sodium, rubidium is larger than calcium, cesium is larger than rubidium. So again, going down that group, if I pull up a periodic table, walk over here, so lithium, sodium, potassium, rubidium, cesium. So we're just saying going down the periodic table, in the same column, atoms get larger. The radius increases. Or sorry, yeah, the radius increases. But we can also see from this chart, again, if I go across the periodic table, so if I start at lithium, and then I go to beryllium, and then boron, nitrogen, carbon, nitrogen, oxygen, fluorine, and then neon, the size generally gets smaller. There is a little bump there. Let's see, the lithium, beryllium, boron, carbon, nitrogen, and then from nitrogen to oxygen, it bumps up a little bit, and then it comes back down. This is what I was saying. We're talking general trends. So if I ask you to compare two things that are next to each other on the periodic table, use the general trend, or I'll give you a chart like this with sizes, and you can use that. But most of the time, we're going to be talking in terms of general trends. Your question? Two questions. First, lithium's bigger than neon, yeah. I don't remember. Yeah. Probably has to do with pairing. But if we're looking at main group elements, the biggest, broadest trend to remember is that at the top right of the periodic table, we have the smallest elements. And at the bottom left, we have the largest. In general, going down will get larger, or going left will get larger. Anything that takes me closer to that bottom left corner. Anything going to the right or up will be smaller. Cool, so that's a trend, but I don't know, we talked about, I think at the beginning of this chapter, why? Why does it get smaller as I go across? Why does it get larger as I go down? Any guesses?
I was thinking that's why I was asking.
Oh, because of weight? No, it's related, but yeah.
So it goes up and to the right, it gets stronger.
Yeah. Has to do with the attraction being felt by the electrons on the outside, actually really all of the electrons, and the nucleus. So more nuclear charge will pull the electrons closer, making the whole thing smaller. So shielding is really the reason that things get larger as we go down, because for every row that we go down on the periodic table, we add another shell. And all of those electrons in that outermost shell are going to be shielded from the nucleus by the core electrons. So they're going to be blocking that nuclear charge. Because we got a positive nucleus in the middle, and then as I add electrons, or as I add shells, so maybe this is n equals, what is that? 1, 2, 3, 4. Right? Every shell gets farther away, and it feels less of the pull from the nucleus. So that shielding causes those outer electrons to not experience that full strength of the nuclear charge. So I think I mentioned it earlier. I think it's on the next slide. But Z effective, so effective nuclear charge. So we look at a bunch of different electrons around just lithium. Keep it real simple. This 1s electron is a core electron. And it's in the 1s shell. So it's pretty close to the nucleus. It's feeling the full 3+ charge from the nucleus. But if I go and I look out at this valence electron in the 2s orbital, it's farther away. And not only is it farther away, but these electrons that are inside are blocking the nucleus from that outer electron. So if it helps, you can think of the nucleus as like a campfire, bonfire. If there's people standing between you and the fire, you're not going to feel as much of the heat. Kind of works like that. And so we're going to just calculate it as simply as possible. The effective nuclear charge is the actual nuclear charge, which is just the number of protons. So for lithium, it would be +3 or 3+. I guess I should put 3+. 3+ minus however many core electrons there are. So in lithium, there's going to be 2 core electrons, so our Z effective ends up being 1+. Meaning the valence electrons only feel a 1+ charge from the nucleus. It is a little bit more complicated than that, because we've got these overlapping orbitals, and the number of electrons in those other orbitals also shields just a tad. But the biggest effect is just from how many core electrons there are. So if we look at nitrogen or argon, I'm going to change this. I want to do nitrogen and neon. So nitrogen has how many protons? 7. So nitrogen's going to have 7. Now, how many valence electrons does nitrogen have? 5. So how many core electrons does it have? 2. We'll have 2 core electrons. So we'll do 7, positive 7 minus 2. So that's an effective nuclear charge of 5 plus. And then if I do neon, how many protons does neon have? 10. And how many core electrons does neon have? 2. Still just 2. Neon's effective nuclear charge is going to be 8 plus. And which of those two is smaller, nitrogen or neon?
It's the nitrogen, that's 3 and the 2p. They split up between the 2px and 2y to be the.
Ah, makes sense. So which of them is larger, nitrogen or neon? Using just general trends. Which corner is the small corner? This one. So that one's the large corner. So is neon closer to the small corner or the large corner than nitrogen? Small. So neon is smaller than nitrogen. And the reason is effective nuclear charge. So remember, the electrons have negative charges, core is a positive charge. So the electrons around nitrogen, they're only feeling a 5 plus charge, whereas the electrons around neon, the outer electrons, valence electrons, are feeling an 8 plus charge. So it's like having a stronger magnet and it pulls them closer to the nucleus. So as you go across, the effective nuclear charge increases. I want to compare one other one here. So compare arsenic to nitrogen. So for arsenic, how many protons does arsenic have? 33. Arsenic has 33 protons. How many electrons does arsenic have? What? I was saying just electrons total. 33. Now how many core electrons does arsenic have? 28. Because the valence electrons are going to be the 4s2 and the 4p3. The core electrons will be all of the same electrons that argon has, plus the 10 d orbital electrons. Oh, that was hard to say. Brain really wanted to say dorbital. So it's got 28. So 33 minus the 28 core electrons is still an effective nuclear charge of 5 plus. But now if we think about size again, so nitrogen was larger than neon. So why is arsenic, I guess, is arsenic larger than neon? Yeah, it's farther down. But why, if the effective nuclear charge is the same? Yeah, it has more shells because arsenic is farther down the periodic table. So nitrogen only has n equals 2 shell, whereas arsenic has n equals 3 and then n equals 4. So we've added these other shells. So going down a periodic table, it's the shells that make them larger. Going across left or right, it's the effective nuclear charge that makes them smaller or larger. Okay. I will probably have you calculate effective nuclear charge because if you know what you're doing, it's pretty easy. Protons and then core electrons. The size changes because of the number of shells. Hypothetically, maybe. Are we going to see that happen? No. No, I don't think it can be negative. But again, that's a real edge case thing. So again, moving down a column, the principal quantum number increases, meaning that we add shells and the orbitals are larger. So it gets bigger. Moving across the period, the Z effective increases while N is the same. So we stay in the same quantum shell, but we add more protons to the nucleus, increasing the effective nuclear charge. And then because we have a stronger difference in charge, we have stronger attraction between the core and the valence electrons. Yeah, and like in Chem 20, that's what I say. Because in general, yes, but I'm sure we could find exceptions on the actual chart of actual sizes. If there was, actually I think we have, yeah, we're gonna do one, but I think Alex, and I gotta think about Alex when I'm teaching this too, Alex will say if it's down one and it's to the right one, then that cannot be determined with the information available, just based on their positions. So I'll show you what I mean in a second. Oh, transition metals. The transition metals are weird. So like in the middle of the periodic table. But again, they increase in size going down a column, just like the main group elements. But really going across, they stay the same. And this is because we basically just have two valence electrons the entire time, and we add core electrons. So the effective nuclear charge, because for every one core electron we add, we also add one proton. The effective nuclear charge doesn't really change all the way across the D block. So their sizes are basically the same, unless you change the number of shells and go down. All right. So if we compare tin or iodine, which one's larger? Why tin? Yeah, it's more to the left. So iodine is going to have a higher effective nuclear charge. Germanium and polonium. Why germanium? It's more to the left, which would make it larger, but polonium's farther down. If I was doing this on Alex, I'd say can't determine, because it's the same number of moves. Right, so this is 2 steps down, it's also 2 steps to the right. I think Alex would take that to be can't be determined. If I was to take a guess, like my best guess as to which one was larger, if I absolutely had to choose, I'd say polonium's larger because it added 2 more shells. So in essence here, we're really weighing, just using the very general trends on the periodic table. Is it moving to the right more, or is it moving to the left more, or is it moving up more or down more? And so you could just count those and say going down makes it bigger, but going 2 to the right makes it smaller. So because it's 2 down, 2 right, those cancel each other out basically. I don't know if that other chart went that, I don't think it went that low. All right, so now chromium or tungsten. Yeah. Now what if I said chromium and iron? So if I said chromium or iron, can't tell. For the transition metals here, so if we calculate the effective nuclear charge, this is going to be 24, right? 24 protons minus 18 core electrons, to go back to argon, plus another 1, 2, 3, 4 core electrons, so 22. So that would be about 2 plus. Now if we do, iron has 26 protons, but how many core electrons does iron have? 24, because it'll be 18 plus 1, 2, 3, 4, 5, 6, which is 24. So that's also 2 plus. Because these are all going, all these electrons that we put in here are going into the 3D orbital, which is not a valence shell, or it doesn't add to the valence electrons. One more proton is one more core electron. For any of the transition metal elements, if you're going left to right, just got to say, can't say, because the effective nuclear charge is the same, at least the basic effective nuclear charge. You can just say down a row or down a column is going to be larger. So it can't be determined. I think that covers every case of a question I would give you. Did you get hit? Oh. You should get that looked at. All right, so we look at electron configurations of ions, right? So we got anions form when we gain electrons, right? Adding electrons, more negative charges. Cations form when we lose electrons from the valence shell to subtract charges or subtract electrons. For example, aluminum, why is that? That's not, oh, I see. This is the aluminum Al3+, because I was looking for this. So aluminum has these 3s2 and then 3p1. So there's 3 electrons there. And in general, when we're doing electron configurations for cations, you remove electrons in reverse filling order. So the 3p1 and the 3s2, those are the last electrons to go in. So to get back to the same electron configuration as neon, we have to lose 3 electrons. So the 3p1 and the 3s2, those 3 electrons we lose, which would have been these empty orbitals, or these now empty orbitals. So we empty out those orbitals and we remove that shell. So if I remove a shell, how's that going to change the size of aluminum? It's going to be smaller. It's going to be way smaller, because we also change the effective nuclear charge being felt by the valence electrons. Because now all of these electrons out here, they were being shielded by these 8 inner electrons. But as soon as I get rid of these 3 electrons, now the 2s2 and the 2p6, those are the valence electrons. And they're only being shielded by 2 electrons in the 1s orbital. Ah, yes, for transition metals, so main group metals are a little bit easier. The transition metals, you remove the valence electrons first, even if it's not necessarily the reverse filling order. Normally, when you're filling in the electrons, you'd probably go 4s2 and then 3d6. But for iron, the first electrons that get lost are the 4s electrons. And then if we do the Fe3+, then you would also lose one of the 3d electrons. This goes from 3d6 to 3d5. I think it's easier to see this if I do. So if this is 4s, this is 1, 2, 3, 4, 5. 3ds, those would be 1, 2, 3, 4, 6. So that'd be the orbital diagram for iron 2+. And this actually nicely illustrates why iron forms a 2+ and a 3+ charge. Because iron loses these 4s electrons first, loses those valence electrons because they're in the outermost shell. So they're the easiest to lose. That empties this out. The other ion that it could form is the 3+, because here we've got one set of paired electrons. So if I lose one more electron, then that makes all of my d electrons unpaired, which is extra stable. All of this to say that when you're doing a cation, electron configuration cation for a transition metal, remove valence electrons first, and then d orbital electrons. I think honestly we could summarize this even better. Instead of just saying reverse filling order, just say remove valence electrons first. Ah, yes. All right, so you guys know that some metals, some things are magnetic, usually metals. Probably never experienced something that wasn't a metal and was magnetic, but also some things aren't. The thing that makes a metal, bless you, magnetic or not, is this property of paramagnetism. If an atom or ion is paramagnetic, that magnetism, that paramagnetism, is caused by unpaired electrons. Because those unpaired electrons generate their own sort of mini magnetic field, which allows them to interact with other magnetic fields, and they're attracted to them. Now, diamagnetic atoms or ions have electron configurations where all of their electrons are paired, and they're actually slightly repelled by a magnetic field, which is not something that you really see because it is very slight. Magnetic atoms, electrons are paired. And this is where you really got to draw orbital diagrams to see it. All right, so electron configuration, orbital diagram for each ion, and predict whether each will be paramagnetic or diamagnetic. Let's see. Oh, good, that's what I was going to do. So we're going to do cobalt. So cobalt's here. So the easiest way to do this is do cobalt first and then subtract, or you say, if I want to do cobalt, but I want to do cobalt 2+. So cobalt 2+. That 2+, what does that 2+ mean in terms of my number of electrons? 2 fewer electrons. So in the periodic table, I can look at my periodic table and say, okay, cobalt's here. What element has 2 fewer electrons than cobalt? Manganese. When I do cobalt 2+, I can do the same electron configuration for manganese. And now we're really only concerned about valence electrons, but we got to remove the 4s electrons first. So we're only concerned about valence electrons, so we can start with argon. It'll have a similar, it's got the same number of electrons as manganese, but this will be slightly different. Because it'll be argon, and then it'll be 4s, it would be 4s2, 3d. Let's see this, 1, 2, 3, 4, 5, 6, 7. So 4s2, 3d7 would be cobalt, no charge. But which electrons do I remove first? The 4s electrons. So these get removed first. So the electron configuration would be this. And I would say argon. And actually with that, now we can say is just going to be 4, 5. Yeah. So is cobalt 2+ going to be paramagnetic or diamagnetic? Paramagnetic, because we have unpaired electrons. Okay. Now, for nitrogen 3-, let's see, it'd be helium. And then what would the electron configuration for N3- be? Nitrogen. Be 1, 2, 3 more electrons. So it'll be the same as neon. So this will be 2s2, 3p6. Is that going to have any unpaired electrons? It shouldn't, because the valence electrons are all filled. This is 1, 2, 3, 4, 5, 6, 7, 8. So paramagnetic or diamagnetic? Diamagnetic. So for electron configurations or orbital diagrams of ions, you just add or remove electrons depending on what the charge is. Just remember when you're doing cobalt that you need to remove them from, or if you're doing a transition metal, they come out of the 4s first, and then the 3d. Times it. All right, this took longer than I thought it would. Good on this? I think that's the only other thing that we really have to calculate at this point for the rest of these slides. We talked about, yeah, cations being much smaller because we completely lose a principal shell. And on top of completely losing a principal shell, we also get a higher effective nuclear charge. So I think if we looked at, let's do sodium. Oops. Oh, and you'll probably quickly pick up on the trend for effective nuclear charge. What's the effective nuclear charge for sodium's valence electron? +1. 10, so it'd be whatever the atomic number is minus, for main group elements at least, I guess You got to subtract out the d electrons. For a lot of these above the d orbitals, though, it's just whatever number of electrons it has minus the previous noble gas. So sodium is going to be 11 minus 10, so it's going to be 1 plus. Like that. But if I take that to sodium plus, so with a 1 plus charge, this 11 hasn't changed, because that's just the number of protons. But now how many core electrons does Na plus have? So it's got the same electron configuration as neon. So now the only core electrons are the ones represented by hydrogen and helium. So there's only 2 core electrons. So the effective nuclear charge would be just minus 2. And so this is now 9 plus. So not only do we lose that outer shell, it also drastically increases the effective nuclear charge. Because now all of those previous core electrons, or some of them, become valence electrons. So you see really big jumps. So sodium jumps from 186 down to 95. So it cuts the size in half. So going the opposite direction, anions get much larger than neutral atoms. So nucleus doesn't change, but you add 1 or more electrons, and you get a lower effective nuclear charge. Now, if you calculate this the way that we've been doing it, it might not, if you calculate the way that we've been doing it, you won't see that. So if I take something like sulfur, so sulfur is going to be, it's got 16 protons minus 10 core electrons, so that equals 6 plus. Sulfur 2 minus still has 16 protons minus still 10 core electrons, so it's still 6 plus. So this is where the effect of just having lots of electrons in the same orbital, they actually shield each other a little bit. This 6 plus with these 2 extra electrons will actually be less than the effective nuclear charge of sulfur without those 2 electrons. But the book only calculates it like this, so the thing you need to know is that we complete that shell, we lower the effective nuclear charge, and so that makes them larger. If you were ever to compare, actually I think, yeah, okay, we'll do that one. So if you ever have to compare 2 things, just know cations are losing an outer shell, so they get smaller. Anions are gaining more electrons without changing the effective, while slightly lowering the effective nuclear charge, so they get larger. So these are isoelectric ions, meaning that they have the same number of electrons. So all 3 of these. But you're going to have really big differences in nucleus or radius because you've got differences in effective nuclear charge. So adding 2 electrons makes sulfur larger than chlorine because, again, there's that in-shell shielding of nuclear charge. So it's a little bit larger, but if we go from like chlorine to potassium, is a lot smaller than chlorine because higher nuclear charge, and calcium's even higher.
You said that cations are smaller than the shell.
Yeah.
Like a cation doesn't show. You know what I'm saying?
Oh.
Because you can't really think about it as the atom before.
Yeah. So like I said, though, so if it was like Mg plus, only loses 1 electron instead of 2, would that be smaller or larger than magnesium? No charge. It'd be a little bit smaller. Not as much as going from magnesium to magnesium 2 plus, because you're right, you don't lose that shell. But just like the difference between chlorine and sulfur, or I guess sulfur 2 minus and sulfur no charge, we're adding more electrons into the same shell. There is a little bit of shielding that happens from those electrons, even within the same shell. So here we would lose 1 of those electrons. Now we've just got the 1 by itself. So it would be experiencing a slightly less shielding. And so Mg plus, I would expect to be smaller than magnesium. Between magnesium, Mg and Mg plus, the number of protons is the same. So here I'm just saying, this is saying that when I was saying cations are always smaller, they're always smaller than their uncharged nucleus. Because obviously you can have, like fluorine might be, but if you went down to like rubidium 2+, which is really huge, even without its 2 electrons or 1 electron, fluorine is still going to be smaller. So this is just comparing calcium 2+ to calcium, potassium plus to potassium in terms of cations get smaller, anions get larger. So with that in mind, potassium or potassium plus, which one's smaller? Or wait, larger. Which one's larger? Potassium. And why? There's 2 reasons. Yeah, so why is the cation smaller? You lose an outer shell. And what else does losing the outer shell change? Shielding. Effective nuclear charge. So I go from potassium, if it has 1 electron here, that 1 electron is being shielded by everything in the third row. But if I get rid of that electron, now those third row electrons, or the electrons I should say that maybe that are represented by the third row, are now the valence electrons. And so they're only being shielded by any electrons inside of that. Does that part make sense? No? Okay. So let's see, that's 1, 2, 3, 4. Super simplified diagram, right? More Lewis structure, less actual structure of orbitals, because I'm drawing them more like orbits. All right, so that's potassium. All right, so this 1 electron out here is the valence electron. Is being shielded from the nucleus by all of these ones in n equals 1, n equals 2, n equals 3. Right, so a lot of shielding. Now, when I make this K plus, that gets rid of this electron, and it gets rid of that shell. So now my valence electrons are just these n equals 3 electrons, and so they're only being shielded by n equals 2 and n equals 1. So we basically shift everything and say, oh, these aren't core electrons anymore, so they're not participating in the shielding. Only the ones inside of them are. And that's what's happening for every one of these cations. Yeah. The outer layer leaves. No, it's more secure than the 4th level was. So like when I get rid of that outer one, it was being the 3, 2, and 1 were all blocking it from the potassium. When I get rid of that one, because when we talk about effective nuclear charge, it's the valence electrons and how much they feel the pull of the nucleus. So if I get rid of that 1 electron, my valence electrons are now just the n equals 3 electrons. So then it's however many n equals 3 electrons, and then I subtract out just the electrons inside of that. So it goes, what's the potassium was 19. So this would be 19 minus 10 to get plus 9. I think once this picture makes sense, it makes this, I guess, in my opinion, pretty easy. So now this 4, these n equals 3 are also core electrons. So then that's, instead of being 10, is 18. So it's 9 minus 18 equals plus 1. That's for this, that's huge. That's for this one, and this is for these. We changed what the valence electrons are. Potassium has 19 protons. So this is the Z, and then this is Z effective. There. So then, which one's larger, fluorine or fluoride? F minus. Fluoride, because we add another electron, increases shielding a little bit. And then how about calcium 2+ or chloride minus? Why would it be uncertain? Yeah, so these are both isoelectric. And really we could compare effective nuclear charge here. So calcium and chloride, calcium's losing 2 electrons to have the same as argon, whereas chloride's gaining 1 to have the same as argon. But calcium has a nuclear charge of 20 minus 10. So that's a plus 10 Z effective. Whereas chloride is 17, it gains 1 more electron, so it has 18 electrons, but the 17 is the number of protons, minus 10 is only plus 7. So the calcium 2 plus has a much larger effective nuclear charge, which makes it larger or smaller.
I think I'm so confused, like, how did you get the 10? Like, how do you count that?
Oh, the number of core electrons.
How do you get that?
So the number of core electrons, the quick way to do it for most things is you could say, here, I'll do, so if I do the electron configuration for Ca2 plus, it will be, oh, here, I'll do the whole thing. 1s2, 2s2, 2p6, 3s2, 3p6. So the core electrons would be these ones. Does that part make sense?
Yeah.
Good on that, right? So those are all the core electrons, and so that's 10.
Okay.
Now, the other way we could do this electron configuration is if I did neon, and then I said 3s2, 3p6. Because neon's electron configuration, neon's electron configuration represents 1s2, 2s2, 2p6.
Okay.
So as long as we're not talking about d electrons, anything that has d orbital electrons, those are core electrons. So we have to include those for shielding. But just talking about calcium, then I say, okay, calcium 2 plus has the same number of electrons as argon, but the core electrons would be represented by neon, and that's got 10 electrons. Okay. Any other questions? Oh yeah, calcium 2 plus or chloride minus, which one's larger? Cl2 minus, Ca2 plus. So here we can compare them with the effective nuclear charge. Because higher effective nuclear charge, they both have the same shell. N equals 3 is full. Calcium has a higher effective nuclear charge, which is more strongly pulling on those valence electrons, which makes it smaller. So chloride would be bigger. If it's isoelectric, meaning if they're the same number of electrons, and the effective nuclear charge is higher, then it's smaller. Yeah, really effective nuclear charge is the whole thing. That or a number of shells. Okay. Real quickly then, we got ionization energy. This is the energy to remove an electron, specifically from an atom or ion in the gaseous state. So a lot of times you can take whatever the name is and derive a lot of meaning from that. You can derive some from this. Right? Ionization energy doesn't sound specifically like removing an electron. It just sounds like it's the energy to make an ion. When we're talking about it in terms of chemistry, it's the energy to remove 1 electron. And it's always to remove an electron. So this energy is always going to be positive because it always takes energy to move an electron away from the nucleus. So it goes to a higher, you have to give it energy to get it away from that energy sink. And so we can have the first ionization energy, IE1, is to remove 1 electron to make a 1 plus charge. The second ionization energy would be then taking away another electron. So you put some energy in to get an electron out. And these have trends. And again, You can determine these, but what I want you to know is the general trends. You don't need to memorize specific ionization energies. In general, first ionization energy decreases going down a group. And this is because, really simply, the valence electron's farther away from the nucleus. Right, so as I put more shells, that puts more space and more shielding between the nucleus and an electron on the outside. It's also the same reason that energy levels, n equals 1, the energy levels around an atom's nucleus start to get closer and closer together as you go up. So we saw that with the electrons and how they can be excited and then relax down to lower energy states. What we're doing with ionization energy is basically exciting it out of the atom. So what's the minimum amount of energy to eject one of those electrons? So as we go down, things get larger, the electron's farther away from the nucleus, it's easier to remove. And then as you go across from left to right, the ionization energy generally increases. And that's because effective nuclear charge increases. I'm adding more protons to the nucleus, but not adding a significant amount of shielding by adding more electrons. Bless you. So this is very similar to the same reason that atoms get larger, the atoms get smaller. Right? It's related to size. And since we're talking about electrons being removed, the largest atoms and those on the left side, the largest elements on the left side of the periodic table, are going to be the easiest to remove electrons from. They want to lose electrons already, because if rubidium, cesium, potassium, if they lose a single electron, then they've got a more stable electron configuration. So again, we could say this is the lowest ionization energy, and this would be the highest. So it's really the opposite of size, where the top right is the smallest and the bottom left is the largest. Okay. And again, just using general trends, is tin or iodine going to be easier to ionize or have a lower, sorry, we want the highest ionization energy. Which one's harder to remove an electron from? Iodine. And there's like a few different ways. If you could just remember the trends, the top right's the hardest to remove from, but we can also think about iodine wants to gain an electron. So removing an electron from iodine is going to be really difficult. So it'll be harder to remove an electron from iodine. How about calcium or strontium? Why? It's higher, which means that the electron we're removing is in n equals 4, so it's closer to the nucleus. And so we've got to pull it farther away from the nucleus. So calcium will be higher. How about carbon and phosphorus? Yeah, same. We would say can't be determined. Yeah. You could maybe make an argument that phosphorus is closer to would rather gain 3 electrons, whereas carbon's kind of in the middle, so it's on the fence. So maybe phosphorus has a higher ionization energy, but would say can't be determined. And then how about fluorine and sulfur? Yeah, definitely fluorine. All right, and so this is a situation where the trends match. Moving to the right increases ionization energy, moving up increases ionization energy. So fluorine's definitely higher energy. Okay, so we'll come back to these. We talk about, yeah, we'll come back to this.